There are many ways to decarbonize natural gas power plant. The general approach is using carbon capture, but natural gas also can be replaced by hydrogen. So, what if hydrogen replaced the natural gas in a natural gas combined cycle power plant? Is it affordable, or is it quite technically feasible? And hello everyone, I'm Azaria Haykal Ahmad from Institut Teknologi Bandung, Indonesia. And in this video, I will present to you the paper with title Decarbonizing the Natural Gas Combined Cycle Power Plant by Blue Hydrogen Co-firing and Carbon Capture. The energy industries contribute the largest sources of greenhouse gases, and most of the electric power in the world is dominated by fossil fuel, especially the coal and natural gas. Therefore, there is need for non-carbon fuel integration as one of the decarbonization strategy. And one of the non-carbon fuel that has many advantages is hydrogen. Hydrogen has many benefits, such as high combustion performance, a broad range of production, and there's a broad range of utilization methods, and also high conversion efficiency. Usually, hydrogen is divided into three: the gray hydrogen, blue hydrogen, and the green hydrogen. The gray hydrogen came from the fossil fuel without carbon capture, as you can see in this figure. They are emit CO2 higher than the fossil fuel combustion. And if this hydrogen is use carbon capture, it will be the blue hydrogen. And right now, the cost of the gray hydrogen is the lowest, followed by blue hydrogen, and the last one is green hydrogen. Hydrogen can be used as the co-firing in natural gas power plant. In the Takasago plant, 13 megawatt has quite good result. The hydrogen power plant will increase the NOx, nitrogen oxide emission, but will lower the CO2 emission because the high combustion temperature, but still in operation range. And also by these two experiments, we know the maximum stable operation is about 13% of co-firing. Therefore, in this paper, I have objectives to simulate the hydrogen co-firing in existing 14 megawatt natural gas combined cycle NGCC until 20% calorie or 30% HV with Aspen Plus for version 12.1. Also, in here, I will analyze the thermodynamic aspect, the flue gas, and thermal efficiency, and also analyze and estimate the economical aspect. And here the general schematic. The air will be compressed and burned in the combustion chamber with natural gas and hydrogen. And then the flue gas from the turbine will be used for the steam power plant, and it will be captured in the carbon capture plant, CCP. The CO2 will be compressed and the other will be go to the stack. The CCP will need the CO2 compression and also will need the reboiler ducting. And here natural gas combined cycle NGCC modeling in Aspen Plus. We use air gaps for the combustion simulation. The air gaps will minimize the energy gaps needed in a reaction. So the reaction was not needed in the energy blocks. In the simulation also, we assume that the gas power plant, the gas turbine, doesn't interfere the combined cycle power plant, and also assume with the constant turbine inlet unit. So it will be iterated. Therefore, the flue gas under the turbine, after combustion, the temperature is same. In this study, MEA is used due to the maturity and also it's common in an industry right now. In MEA, there will be need heat to separate amine, and also there is energy penalty from CCP, carbon capture plant, and that energy penalty, the thermal and the electricity one, can be calculated with this equation. Also, in this CCP, I assume that the reboiler of CCP to heat the steam and heat the amine use the NG or natural gas with that efficiency and that emission. In the study also, for the economic modeling, the blue hydrogen is used because it has less emission. And also, the economic is the intermediate, higher a little bit than the gray hydrogens. And the cost of blue hydrogen and natural gas is obtained by average data from EAA 2019. The capacity factor is assumed of 85%, and the electricity price is based on PLN. Because I'm from Indonesia, that is 74.5 USD per megawatt hour. And here the simulation input. Here the composition of natural gas, mostly from methane, CH4, and is the parameter of the natural gas, air inlet compressor, and air outlet compressor. And for HRSG, this is the input, and for the validation, it has lowest error of 0.16%, and the highest one is 6.5%. So it can be considered as the real condition one because the error is below 10%. And here the thermodynamic analysis. This graph is shown the net power of hydrogen co-firing with and without carbon capture. Without carbon capture, the net power is decreased. This is caused by the less mass rate as shown as in this graph. This is because in this simulation, I use constant thermal inlet rate. The HHV of the fuel, the hydrogen and natural gas, is constant. And we know that hydrogen has much higher HHV than natural gas. Therefore, the mass rate of hydrogen will be less than the natural gas one. Meanwhile, with CCS, this graph, the net power will be higher, even though it will be lower for about 2 megawatt, 2.5 megawatt due to energy penalty. But it will increase the net power due to lower energy penalty. So when we use CCS, carbon capture storage, the net power is increased due to the decrease of energy penalty is much higher than the decrease of the energy due to mass rate. And the thermal efficiency for hydrogen co-firing with CCP will be increased per hydrogen co-firing, but it will be decreased for about 2.8% due to energy penalty for about 2.5 megawatt at the last time. And also the stack temperature also will be decreased due to less flue gas flow rate. And the flue gas emission, the NOx will be increased. This is same as the literature one. The NOx will be increased due to OH radical that exists when the hydrogen factor in fuel is larger. And this OH radicals will contribute to NO production. That NO is one of the NOx. Meanwhile, for the CO2 emission, will be decreased due to less carbon carrier, that is natural gas. Then we move on into the carbon capture thermal energy penalty. The CO2 is decreased due to use of hydrogen. So the CO2 capture will be lower and then the reliability will be decreased. The CO2 mostly from NGCC. This is due to assumption of CO2 capture rate is for about 90%. So variable emission can be neglected. And here the economic analysis, that is the capital cost is decreased due to less of CO2 capture. And we know from this graph at 13% coefficient ratio, most of the capital cost breakdown is came from CCP and labor capital. Therefore, with higher hydrogen co-firing, the capital cost will be lower. And meanwhile, this graph is on the CCP capital cost based on CO2 capture per year in million ton per annual. And the next one is the operation and maintenance. We know that by this graph, the operation and maintenance will be increased. Its hydrogen co-firing rate is higher. This is because the hydrogen cost is higher than natural gas, even though it will have same HFC input. As we know in this graph, this is the comparison graph, yeah. At 0% is about 11 million, is about 15 million. And then the natural gas will be lower and lower and lower, but the hydrogen rate of increase is higher than natural gas decrease. So hydrogen cost is one of the biggest factor in this co-firing. And the last one is the gross revenue. The gross revenue is came from the revenue minus the operation and maintenance cost. We know that the use of CCS will decrease gross revenue for about 13% from the 6 million to the 4 million. And the maximum hydrogen co-firing rate is about 23%. That is the gross revenue equal to 0. But we know that the most influence one is the hydrogen cost, not the CCS. So we will be next into the further discussion. In the beginning, the blue hydrogen was used. The blue hydrogen that came from natural gas is used. But with this graph, we know that the hydrogen cost will decrease in every year. But you know, from the natural gas, the blue hydrogen from natural gas is likely same for each year until 2050. But the green hydrogen will be lower and lower every year. Therefore, the use of the green hydrogen in the future will also decrease the cost of NGCC co-firing. And here the sensitivity analysis for the hydrogen cost and also the natural gas cost. Hydrogen co-firing is better than the natural gas plus carbon capture in the cost of 0.9 USD per kilogram H2 hydrogen, and natural gas cost is 6 USD per gigajoule. And for the next one is for the 13% co-firing. We know that comparing to the 10% co-firing, there's an increase of influence of hydrogen costs. In the last slide, the gross revenue different from the its cost is only a little bit, but when it's in 30% co-firing, the influence is more higher. And for the condition is a little bit same, 0.9 USD per kilogram hydrogen and 6 USD per gigajoule natural gas. By increase of hydrogen co-firing in constant turbine inlet temperature with constant excess oxygen condition, there will be net power increase in NGCC with CCP. But due to CCP, there will be energy penalty for about 2 megawatt. The CO2 will be lower and lower, but the NOx will be increased, but still below the standard. The thermal efficiency also will decrease comparing to NGCC without CCP. But there will be increase of thermal efficiency per hydrogen co-firing rate increase. There will be decrease of capital costs, but it will be increase in operation and maintenance cost and also revenue due to the increase of the net power. But overall, the gross revenue will be decreased and has zero value at 23% of co-firing rates. And for the way forward, there will be needs of the detailed simulation of carbon capture plant and also simulation in the computational fluid dynamics. The carbon capture plant will be needed for the simulation to know the specific energy penalty in this plant, and also need for the reliability data, right? And for the CFD, it will be need to simulate the distributional temperature in the turbine. And also we can consider it the other option of co-firing, such as ammonia natural gas, ammonia hydrogen natural gas, and etc. And also do the detailed economic study. And thank you. We are from Indonesia, and terima kasih.